stats, intro to stats. And in this video, we're going to get into um, calculating some basic descriptive statistics. And again, I'm going to use a data set that I'll share with you in just a few minutes. So let's get started. So in analyzing quantitative data, uh, I think of our data as either being that we collect as either being quantitative or categorical. Um, and examples of quantitative data: ACT, height, number of false. And categorical data is anything that fits nicely into a slot, like gender, political party, religious affiliation. I notice the students that I work with, the greatest source of confusion is when we give numbers to categorical data. Like it would be reasonable to maybe for gender, for example, to code males as zeros and females as one. But you got to inject a little bit of statistical common sense there, and realize that even though it is a placement of a number, it represents a category. Um, Describing quantitative data, we typically look at three things. We look at measures of center, which are officially called measures of central tendencies. We use the three M's: the mean, the median, and the mode. The mean is nothing more than the arithmetic average. The median is the number that resides in the center when your data set is arranged from low to high. The mode is the piece of data that occurs the most. And we get into measures of variability. What I want you to think about for measures of variability is just measures of spread. And the one measure we use is range, which is just the high minus the low. We also report quartiles and IQR. Quartiles, as you would expect from the prefix of quartiles, it indicates four. So if we cut our data into four equal pieces when arranged from low to high, those cuts are called quartiles. And finally, we report the standard deviation and variance. The graphs that we report for quantitative data are box plots and histograms. And guys, I'm going to give you examples of this later on. So, well, no, I'm going to give you an example of it right now. Age was a variable that we collected in this fall study. So I calculated the three measures of central tendency. The average age was 81.19. When I ordered all the ages from low to high, the age that was smack dab in the center was 82.5, and the age that occurred the most was 85. Now, starting this journey with me in analyzing data, you knew nothing about the data set other than it dealt with some fall. Now that we have measures of central tendency, the mean, median, and mode, you can tell that we have a quite elderly group of subjects in the study. Now, the measures of variability again focus on how much do our data, what's the spread. The range gives you the simplest measure of spread. The oldest person in our study was 100. The youngest person in our study was 62. So subtract those, you get 38.00. And you got to step back for a second and notice that all the measures of central tendency and variability, I am consistent in presenting these to two places. It drives me insane because it's such an easy fix when students aren't consistent in reporting these measurements. So it's pretty standard to report these to two places. Now the quartiles, again, if you think about arranging our data from high to low and we cut our data into four equal pieces, there are three cuts to accomplish that. The first cut is Q1. Our value for Q1 is 75. That tells me that approximately 25% of the subjects has ages 75 or lower, and approximately 75% of the ages are above 75. Q3, 87. That tells me that approximately 75% of the ages are below 87, and about 25% of the ages are above 87. The IQR gives me the range of the middle 50% of the data. So we have a range of about 12 for the middle 50%. Now the IQR is a very helpful measure of variability of spread when we have outliers. And guys, we'll talk about outliers throughout this process. Outliers are measurements that fall kind of outside the normal realm of scores. There are ways to calculate those that we may get into, but typically, if we want to see if we have outliers, we examine the data and do a box plot. Guys, our variance is 68.94. Now, the standard deviation and variance in isolation of other information is not really helpful. But if I was to look at another study that dealt with age and I had a standard deviation of 10, then I could say, well, there's more variability in the ages of the subject in the other study than there is mine. So standard deviation gives you a measurement of spread that's comparable across different distributions on the same scale. Box plot for age, when I look at that, I see a pretty symmetric distribution. What I see on the top is pretty much what I see on the bottom. I don't have outliers. If you have outliers in a box plot, you're going to have isolated dots. And we might run into that in a future data set or a future variable. Histogram for age, when I see that, I don't see skewness. Skewness is when your top bar is the highest. I'm sorry, your left bar is the highest and you have a decreasing pattern, or if your last bar is the highest and you have a decreasing pattern to the left. I see a pretty symmetric distribution, so that's something that, just eyeballing a histogram, that's something I look for. Now let's switch to describing false status. False status is either they fell or they didn't, and in this case there were 3 people who didn't report a false status. So false status is, again, categorical, so we report frequencies and percentages instead of means, medians, and standard deviations, because it would make no sense whatsoever to report a mean for fall, because even if I coded these as zeros and ones, it doesn't mean anything, because yes and no is not additive. Yes is yes and no is no. So I report those. There were 127 patients, 44.7% of those who fell reported at least one fall, and there were 154, 54.2% of our sample reported no falls. We had 3 subjects that didn't report a false status, and that was 1.1% of our sample. They got to step back for a second and again keep the eye on the bigger picture here. The bigger picture, when we're describing a variable, statistically describing a variable, we're talking about the subjects in our sample. Now we'll get into this fancy schmancy stuff soon enough, where we're going to take this information and try to generalize to the larger population. We're not there yet. We're just describing the patients who we have data on for this particular study. One of the charts that we do for categorical variables is a pie chart. Pie charts are really, when you only have 2 classifications, in this case, yes or no, they're not that interesting. But nevertheless, you can see that the biggest part of the pie goes with the no's, and the smallest part of the pie goes with the yeses, so gives you an indication where the classifications fall. Bar chart for false status gives you even a better indication of this. So we could follow the top of the bars over to the left axis and get an indication of the frequencies. Now, in getting the ball rolling on this, I wanted to keep it kind of simple. There are ways for us to juice up bar charts and pie charts and put not only counts in but percentages. But I believe let's just kind of start out with the fundamentals, with the basics, and then we can always get fancy. Next thing we probably would want to look at is describing a quantitative variable over a categorical variable, because that seems to always happen. When I get into video, my phone rings. Uh, so to illustrate that, you know, what does age look like over false status? Now, age, again, quantitative. False status is categorical because they either fell or they didn't. So we can see of the non-fallers, the average age was about 81.49. Well, it wasn't about 81.49, it was 81.49. And the average for the fallers was 80.8. So the average age of the ones who didn't fall was a little higher. So you might have thought the other way. You might have thought that the average age of the fallers would have been higher. So that just tells me that age probably isn't going to be a very good predictor of false status. Guys, the median for the non-fallers was also a little higher. I look at the standard deviation, 8.5 versus 8.1. That tells me that the variability in age for the fallers is higher than the variability for the non-fallers, and same with the IQR. If I wanted to provide a box plot, or I'm sorry, a graph, I would do a side-by-side box plot. And you can see here, you can, again, in looking at something like this, you think about the two measures of central tendency and variability. Guys, look at those dark lines in the center. Those are the values for the median. The upper level of the box part, that's Q3. The lower is Q1. And then the top and bottom represents the highest number and the lowest number. So we can follow the dark line over to the left axis and get a pretty good approximation of the medians. But what's most important to me here, when I look at this, is I see that the medians are pretty close, and I see that the variability, the distance from the top to the bottom in both yeses and no, so the fallers and non-fallers, is about the same. So I focus on measures of center, and I focus on measures of spread when I'm looking at these pictures. Next thing we may want to get into, instead of looking at a quantitative variable over a categorical variable, we may want to examine the relationship between two categorical variables. Now, one of the questions, and I've got the questionnaire right here. It says, do you feel unsteady, or do you need to hold on to something when you get out of bed in the morning? Well, when I was coding this, I called that steady AM, maybe for obvious reasons. So is there any relationship between the false status and the response on do you feel unsteady in the morning? So just looking at steady AM, the ones that responded no, there were 178, so about 63% responded no, 37.3 responded yes, and the missing information, luckily there was no missing data here. Now, if I wanted to look at these at the same time, I would do a 2x2 contingency table. And so I can see that 100 out of my 279 reported not feeling unsteady, and they also reported a no. So we can look at the individual components of the 2x2 table along with the sum and column totals to get an indication of the breakdown of false status and steady AM. Now again, we could get fancier with this by reporting percentages, but again, that's just about grinding it out and getting out your calculator and making those calculations. Let's shift now into describing two quantitative variables. Another quantitative variable that we collected that was collected is the number of medications taken per day. So we might want to see if there's a relationship between age and the number of medications. So when I look at a scatter plot, which is presented here, If there's a relationship between the two, the points will be clustered either along a vertical line rising to the right or a vertical line falling to the right. This doesn't show much relation. Well, it doesn't show any relationship whatsoever. There's no linear pattern. It looks like that if you're 90 or 70 or 65, the number of medications that you take doesn't, well, it just doesn't depend on age. Now we come in and we put some numbers, some numerical summaries on these. The correlation coefficient is just a measurement between -1 and +1 that tells us, gives us an indication of the relationship between the two quantitative variables. As the correlation coefficient gets closer to 0, it means that no linear relationship exists. As it gets closer to 1 or -1, it indicates that a linear relationship does exist. Now, a positive, for example, 0.8 and a negative 0.8 indicate the same strength of the relationship. It just indicates that there's a different direction of relationship. So as one goes up, the other goes down. If it's a positive relationship, as one goes up, the other one goes up. Just not much going on here with age and meds. The correlation coefficient is extremely low, 0.13. The coefficient of determination, 1.8%. That tells me that only 1.8%, again, 1.8 out of 100, 1.8% of the variation in the number of meds can be explained by the regression on age. To better explain the relationship, we could create a predictive model, so we could predict the number of meds by taking -0.42 plus 0.07 times the age. So just not a lot going on here between age and meds, but hey, that's the way it works. I know a lot of my master's thesis students, they do a good job of laying out their studies and the focus of their research, and they're all excited about the data collection. They collect their data, they throw it into R and start analyzing the data, and they don't find anything. And they start to think, well, my study's a complete nightmare. It's a disaster because I haven't found anything. Even when you don't find anything, you find something that can contribute to the knowledge of your discipline area. So if I wanted to see any relationship between age and meds, if I wanted to generalize that from this this sample, there's just not much there. All right, let's see how this is done in R. So I'm going to get out of this, and I'm going to get rid of the PowerPoint. And I have a data set that I'm going to share with you guys. And this is the data set that we actually use for the occupational therapy grant, the fall status. Now, one of the things I notice when I look at this, I notice I have a lot of NAs. NAs stand for missing data. And students tell me all the time, they're like, well, Dr. Darby, when I took your stats class, we didn't deal with missing data. Well, from these textbook examples and textbook data sets, you don't have these nuances. But when you get into the real world, you get people that just, for one reason or the other, for example, right here, the subject ID 7 just either refused or forgot to answer or reported something that wasn't legible. For some reason or the other, there's a missing piece of data for this fall. Now, as I look at this, I see that I need to make a correction, or not a correction, but a modification, an edit. We have fall as the number of falls, but when we looked at the design and kind of the intent of the study, we wanted to see whether they fell or didn't fall. So what I would want to do is I would want to go in and go to data. I want to highlight fall, and I want to sort, and I want to expand the selection. That way all the other information will be sorted along and stay with the subject. And then I'm going to come in here and insert a variable called false status. Now, guys, I always like my variables to be capitalized, and I like to keep it at one word because it just makes it easier once we get into R. So zeros where they didn't fall. So I'm going to take this and fill all the way down to the zeros, maybe. So this is why it makes it nice to sort. So all those people didn't fall, and all these people did fall. So much easier with a mouse, but with a laptop this is a little bit harder. All right, this is being stubborn. All right, so right there we have NA. We have an NA, NA. And I got some stuff down there, and I need to just go down here and make sure I don't have any data lurking around. All right, so I've got my data set ready to save. So I'm going to go over here and do a save as. Now, important point here, guys. I'm going to save this as OT data, but I can't insert this data set into R unless I change it to a comma separated values.csv. So now, guys, this is it's not quite as simple on a Windows machine because there's 3 .csvs. Let me. I've got my other computer up here. Let me just see what it actually does come up as. There's a CSV Macintosh, a CSV MS-DOS. Those are the two you don't want. You want the CSV. It's capitalized, comma delimited. So comma delimited if you're dealing on a Windows machine. But I want .csv. Now again, why am I doing this? I'm saving the file in a format that R will be able to read, import in. So I'm going to save it on my desktop for reasons I'll explain in just a second. All right, now I'm going to close it down because I don't need it anymore. It's going to ask me if I want to save it. Nope, I've already saved it. And now I have R open. Now, the very first thing that I'm going to want to do with R is, well, first thing I'm going to do is get it where you guys can see it. All right. First thing I have to do in R is I have to set the working directory. And chances are your working directory is set as something other than the desktop. Now, I have my data set that I want to import into R on the desktop, so that's the reason I have to set it that way. So the first thing I would want to do is get my working directory and see where it's going. Well, it's just going to ddarbro. So I want to set the working directory, and I'm going to use that format. But I'm going to change the last part. Now, some of you might have like users, your name, / documents. Or it might have another location where it's the default is set to go look for the information for the data set. So just change whatever comes after the name part and set as desktop. Now, R works kind of, I kind of like it. Students think that they should get some sort of confirmation, good job, well done, you know. It doesn't do that. It only tells you if you do something wrong. Now, if you're on a Windows machine that is here at the university, here's what you would have to do. You would have to set your working directory, quote unquote, C:\/ users ddarbro desktop. Again, you only do that if you're using a machine at Shawnee State University and it's a Windows machine. Okay. Now I'm not going to put that in because if I do, R is going to give me one of those big red flashing, you messed up kind of warnings. Now the next thing I want to do is I get my data, and I like to keep it simple because I don't want elaborate names for my data set, so I just call it data. And I'm going to use what's called the read.csv command. So that's going to read a .csv, a CSV file. That's the reason I changed my Excel file to a CSV format. In quotations, remember I called that OT data, and it has an extension .csv. Now, if I'd made a mistake, it would come up a warning. It would come up an error. It'll let you know if you make a mistake. So if you didn't get a warning or an error, then all is good. The next thing you have to do to actually get the data set into the processor is you have to attach it. Now, even though you read the .csv from the desktop, and you got it into the kind of the upper layer, if you will, into R, you have to attach it so you can actually take a look at the data. Now, the next thing I always like to do, now if you want to, and if you type data, and I don't want to do this because I don't like to messy up my screen, but if you type data, you're going to get all the information that we saw in the Excel spreadsheet. But I don't like to do that because I don't want to mess up my stuff. I'm very anal retentive when it comes to my data on R, so please overlook me. All right, guys, we've got our data attached. The next thing I like to do is just do names data. This is going to give me my variable names. So I can see that I have, age and fall. Fall status is the variable that we created. We've got the number of meds. We got steady AM. So we have some other measurements that were part of the study. Now, let's think back. What was the first thing that we did in the PowerPoint? We wanted to look at the mean, the median, the mode, the standard deviation, and the quartiles, right? So guys, if I want to look at mean of age, I just type mean, capital AGE. Now, let me show you what happens. A lot of students, they think, well, that's the same thing, right? Well, if you want to drive yourself insane, think that's the same thing. Guys, even though you and I see mean age there as the same thing as that, R sees it as Venus and Mars. Okay? So mean, standard deviation. Now, something I would highly recommend you guys do is create an R code notebook. And there's going to be, you'll probably need about 2 pages of things. So in a future assignment or something, if you need to find the mean of a quantitative variable, you just type lowercase MEAN and then the variable name. If you need the standard deviation, just do SDH. That's going to, or SD, whatever the name of the variable is. It's going to beat you getting, and I'm not sure whether Dr. Raver is going to give you an assignment on this or not, but if she does, it's going to beat going back and rewatching videos. You just open up your notebook and you know the R code. I think next thing we did was the mode. R doesn't have a mode command. It's going to give us an error because it's numeric. But what you can do is you can do table age, and it will give you a breakdown of the counts across age. So this tells me that there was one person age 62, there was one person age 63, and we actually had 2 people age 100. Good for them. So if I look through these frequencies, I can see that 19 is the highest count, and that is associated with an age of 85. So that tells me that my mode age of 85. Now, guys, I'll tell you what. Bear with me for just a second. I want to bring up the PowerPoint on my other computer so I can play right along with what. Okay, where is it? It's not on my other computer. Daggone it. Okay, I think I can remember this. So I think the next thing we did is we looked at the quartiles. And no, we looked at the range, didn't we? So range of age. And we can see that the range gives you, it doesn't give you the range, it just gives you the high and the low. So if we take 100 minus 62, we get the age of 38 that was reported. The next thing we did was we looked at the median, 82.5, and then we looked at the quartiles. Now, if you would think that if you wanted quartiles, you would just type quartiles, but it's going to give us an error because that's not the way we do quartiles. We do quartiles by quantiles. Now the default for, well, that's fun. Okay, there we go. It's actually quantile and not quantiles. So we can see that what it does, it gives us the 5-number summary when we do quantile. The lowest number 62, the highest number is 100. And the numbers at the top, the 0% to 25% to 50% to 75% and 100%, tell us the percentage of our data with ages below the given score. So for example, under 75%, you're going to see the age of 87. That tells me that 75% of the ages are at or below 87. You see 50% is 82.5. 50% of our ages are at or below 82.5. 25% of our ages are at or below 75. Well, guys, this defines what Q1 and Q3 is. So Q1 would be the number at the 25%, and Q3 would be the number at the 75%. If I want the IQR, I mean, really, I can just subtract 87 minus 75, or I can just use this as a calculator to do 87 minus 75. So I think I've run through everything. Well, let's do a box plot. So a box plot just for age. I showed you that one earlier. And a histogram is just HIST. And you can see this is the way we get the histogram for ages. Now the next thing I think I did is I looked into the false status. And I wanted to look at the counts of false status. So to do that, we would do table, false status, and it's going to give me that I have 154 that did not fall or did not report falling, and 127 that reported. Now guys, if you do 154, if you're paying attention, plus 127, if you notice, we had 284 patients because 3 didn't report a false status. So a way of finding how many measurements you have, if you do length false status, that tells you how many entries you have for false status, which matches the 284 patients that we had in this study. So if I take 154 divided by 284, because there were 154 that reported not falling, I can see that I get 54.2%. If I do 127 divided by 284, and then of course if I do 3 divided by 284, I get the 1.1% that I reported. Pie chart. I always forget this. I know it has to be done with table. Yeah. So to get a pie chart, it's just to command PIE. And a bar chart is, I think, bar plot. And it's also fall status. Pretty boring stuff. I mean, really, the bar plots are potentially more interesting if you have more than two groups, but again, potentially, I don't know. So the next thing we did in the PowerPoint is we moved into examining age over fall status. So the first thing I wanted to do is look at the numerical summaries. So to do that, we use what's called the tapply function. Now the tapply function allows me to take a categorical variable and examine the descriptives over a categorical variable. So I want age over fall status, and I have to do this separately for each numerical summary. So if I want to do this for mean, I can see that my average age for the non-fallers was 81.49, and the average age for the fallers was 80.80. Same thing if I want. Now, guys, I can go back up and get my previous command if I just want to edit it, which I do here. So I can hit the up arrow, and then I can just come in here and do standard deviation to get my standard deviations across fallers and non-fallers. Same thing for IQR, and same thing for the median. All right. Next thing I did is I looked at a box plot of my ages over my fall status. Student asked me one time, well, why do you have to put that tilde? Guys, if you can't find your tilde, find your one key, number one, as in 1, 2, 3, 4, 5, 6, find the one key, look to the left of it, and you'll see the squiggly tilde. This will bring up a side-by-side box plot that allows you to compare the distributions across fallers, well, the distribution of ages across fallers and non-fallers. Guys, the next thing we did, we wanted to look at two categorical variables. And so the categorical variable that I decided to do is the steady AM. So what I would do is I'd go back up to my names and I would see, well, how did I code steady AM? Coded it steady AM. So I would probably go table. And the ones who report no's was 178. The ones who reported yeses was 106. Now, if I take 178 plus 106, I can see that I get 284, which indicates to me I don't have missing data. Now, once we get into the big boy, big girl stuff, the inferential stuff, I'll show you a command in R where we can kind of control for the missing data. It's called na.rem equal omit, but we'll get into that soon enough. Okay? Now, but the purpose here is to look at false status over steady AM. So what I would do here is I would do table of false status over steady AM. And I can see that I get a breakdown of the individual components, how many people who reported no on steady AM reported no on falling. So that would be 0 or 100. So, and it's easy to get. I'm pretty sure you can go prop table false status steady AM. No, you can't do that. Okay, why not? Well, I have to get back with you. There's a way that you can go in and have these presented as proportions. I don't know. Maybe, nah, it's not working. I I don't know why I'm worried about this, but this will be the last time I try it. There we go. So I have to do prop table of the table. So I can see that 35.5% of my sample reported no and no. 19.2% reported not falling. Well, guys, once again, the phone goes off. I'll tell you what, if I ever need someone to call me, all I have to do is start putting up a video, and I become the most popular person in the Kentucky, Ohio area. 26.7% reported falling, but reported a no on steady AM. So you can see that it's very, very easy to get the proportions as well. Now, I think the last thing that we did is we looked at the relationship between the two quantitative variables, meds. So if I want to do summary of meds, I get the 5-number summary along with the mean. So it gives me a snapshot. It doesn't give me the quartile. I'm sorry, it doesn't give me the standard deviation, but it gives me a snapshot of the numerical summaries. So I see I have a median of 4 and a mean of 5.39. But if I want to look at the relationship, I would probably do a plot of meds over, that's not right. Let's do All right, guys, hold on for a second. Oh, shoot. I know what I'm doing, guys. I should be doing age meds. First mistake I've ever made right there, and you guys got it. If you believe that, I got a bridge I want to sell you. Again, it doesn't change, right? There's no linear relationship there. There just doesn't seem to be much going on in terms of the relationship between the number of medications taken and the person's age, not their fall status, which is categorical. That's why I got those ridiculous looking plots back there. Now, to get the correlation coefficient, we saw it was 0.13. If we square that and multiply by 100, we get our coefficient of determination 1.8%. To get our linear model, if we want to predict meds from age, all we have to do is just do LM, linear model, put our Y variable first. It would make sense to predict the medications from age, because meds would be more a function of age than age would be of meds. And we can see that you guys probably remember the whole Y equal mx plus b. That's what a linear model, the shape, form, and fashion actually is. So our intercept here is negative 0.42, and our slope would be 0.07. So guys, I know this came at you hard and fast and quick and dirty and everything, but you know, I think I have a total of, well, I don't know, maybe 6 hours to take you through. So, you know, got to make choices on what to go into details on and what not to go into details. So, guys, take care.